we're going to start the debate part. First of all, I'm going to leave it as a open format. I just want to invite Danny and Erik-Jan to respond to each other's introductions, starting with Danny. And when necessary or appropriate, I will introduce some of the statements that are useful. Feel free to ask questions as well through the chat or through other means. Danny, I'm curious as to your response to Erik-Jan.
Yeah, it's actually always nice to hear Erik-Jan talk about these things, and my criticism is always intermingled with a lot of admiration for the JAS program and for the way he has championed that approach. And I'd like to say, as a methodologist, of course, I think that you should get more methods, right? I mean, if it were up to me, you would get frequentist statistics and Bayesian statistics and more. So that's definitely one thing. But in the spirit of the current situation, I want to note actually basically two things about what EJ was saying. And one is the thing that already came up in the discussion while he was explaining it. What are we really looking at? I mean, I really like the pictures, but do we really know what it sounds very intuitive what the probability of the hypothesis is, and that we can really say that the probability that the effect of Adam Sandler's on the box office is. It sounds really, really cool, but do we really get that much more information? And also the fact that people have so much trouble interpreting already this very simple base factor in a very simple design. Are we really getting ahead relative to frequentism? So what is really the added value here? And especially if you get much more complicated models, like, I don't know, three-way ANOVAs, or mixed designs or whatever you have, and frequentism is still always the same interpretation. But, the way the prior and the data combine into a posterior for a complicated model is really complicated. So that's an issue. And the second issue I have is, related.
Wait. Can we do them one at a time? Because
okay,
otherwise I'll just forget.
So you can react. We can just Yeah.
Yeah, I'm reminded of an interview I had. Danny and I, we have the same interviews for grant panels, right? And it's about millions of euros. And once I was, being questioned by somebody, and this person said, "I have a few questions," right? And you have 15 minutes. And at the end, 14 minutes had passed, and she had just fired all these questions at me, right? And I was just writing everything down because I wanted to reply. And then there was no time to answer any of these questions. So I said, well, this is unfortunate because I got all of the tsunami of questions, and I can't answer any of them. And then a person in charge of the meeting just said, well, that's your mistake for not interrupting. So so that's why I interrupted. Okay, so first off, I think it is a little bit confusing to use the word probability when we both mean very different things by it. So you say there can be no probability of a hypothesis because it's either true or false. And as a Bayesian, I would actually agree with that. Within that definition of probability, that's true. But when Bayesians use probability, they mean plausibility. So clearly, some hypotheses can be more plausible than others. And when you have a particular hypothesis and it predicts data better than another hypothesis, it increases in plausibility. So I think it's better if I talk about probability that you think, oh, he means plausibility. And I think that also makes it, easier to understand why it actually makes sense from within the Bayesian paradigm to talk about it like that.
But EJ, why would plausibility adhere to the axioms of the probability calculus? I mean, you're combining these plausibilities of yours with likelihoods and frequency.
Right. Yes.
Values. So why can you do that?
Yeah. Well, there are a series of different axiomatic developments that show that if you want to reason under uncertainty, and if you want to quantify your beliefs, your convictions, your plausibilities, if you want to quantify them by numbers, The only way to do this and not be manifestly silly is to have these things obey the rules of probability theory. Right? And there's many different ways in which you can show this. You can bet on your beliefs. And if you don't use probability theory, you'll be a sure loser. Or you can show that you will get incoherent statements, right? If we say the probability that it rains is 0.7, then the probability that it does not rain has to be 0.3. Anything else is, makes the system explode. So
just to step in here to clarify for the people watching, what Erik-Jan is saying is similar to what we discussed in one of the first lectures, and I mentioned this as the benchmark of rationality and in updating your degree of belief in accordance with rules of probability is what we talked about, and that benchmark is based on the same things Erik-Jan is mentioning now, just to put that in context for you. So, but I also wanted to guide you back towards the original question of Danny.
Right.
Danny's point was that adding Bayesian statistics, he doesn't see
Right.
how adding Bayesian statistics would make things less complicated.
Right. Yes. Well, first of all, I do believe that the advantages I showed in the JASP application were quite pronounced. And specifically, there was a reason why I chose the Adam Sandler data set, right? I wanted a data set where the observer has no control over the process, right? Adam Sandler just continues to do his thing. And you just want to update your knowledge as he produces more movies, right? So, so the ability to keep track of your knowledge and the evidence as the data unfold without your control, because you're not doing an experiment, I think that's a unique advantage to Bayesian statistics, because it's a learning framework and not a decision-making framework. So, I think also evidence in favor of the null hypothesis. I think, it used to be the case that when you were a student and you were doing a project, if your interesting hypothesis was the null hypothesis and you wanted to prove it right, you wanted to show that there was an invariance, that something didn't change across conditions, a methodologist would tell you you're on the wrong side of the null, right? You are making a prediction that you cannot support by data, because you'll get a non-significant p-value if the hypothesis is correct. And what do you conclude then? You don't know whether you had insufficient data or whether the data really support your null hypothesis. And in the Bayesian framework, we can tease those things apart. I think those are really pronounced conceptual advantages.
Yeah, I would not necessarily disagree with the fact that this is a good point about the way the Bayesian does that. Although I would maybe be a bit more hesitant about whether you couldn't do it in another way. I mean, in the end, what do you have? You got to test statistics and you got n, right? And you have a sampling distribution, and you can just reason about this. You can say, well, I had a lot of participants, and I didn't see my confidence interval was really narrow, and it includes 0. Or you can, I mean, right? So I would say it's a bit more shabby. That's probably also what you would say. So the Bayesian thing does this really elegantly, but in the end, it's the same information, right? So there's nothing that goes into the Bayesian framework that isn't just there for us. It's like a chessboard. Right. Everything is in view. I know you like chessboard, so.
Right. Well, no, but I would agree with Danny that a very smart classical statistician can probably draw conclusions that are quantitatively in line with or qualitatively in line with the conclusion that the Bayesian would draw. And in addition, luckily, this debate is important, but luckily what often saves us here is the data. Because if the data clearly show the absence of an effect or clearly show the presence of an effect, it doesn't really matter what you do, right? So the real a lesson underneath here is when you do your internships and when you collect your own data, make sure that you run a good experiment and you collect very many observations, because then it doesn't really matter what you do. But in some cases, you simply do not have that luxury to collect a lot of data, and then it may become important.
So, Jan, to bring us back to one of the statements that I introduced in the video, because what you're saying so far is closely tied to the issue of sensitivity. So how do you talk about having evidence for the null or against the null? And you mentioned having enough participants would mean, in frequentist terms, having a powerful test, right?
Yeah.
So would your reply to this statement be that no, not only Bayesian analysis is useful in interpreting null effects, you can do that with a frequentist analysis as well if your study is properly powered?
No, I would disagree with that. And actually, I wrote a paper about this very topic. And it has the term "the power fallacy" in the title, because what happens is you can, let's say, okay, I could come up with a concrete example, but let's just do it in general terms. Even if you have very many observations and you expect to see a diagnostic result, you could just be unlucky, and for the specific data set you have obtained, there could be no evidence, right? So let's say, okay, I'll give you this specific example. We have 2 urns. One has 5 marbles. 4 of them are white and 1 is black. The other has 5 marbles. 4 of them are white. 1 is blue, right? Mm-hmm. And now you get 1 urn. You don't know which ones, and you draw 1,000 marbles from it. The power in this experiment is huge, right? Because the probability of not hitting the diagnostic marble is very small. But if you happen to be unlucky and you find 1,000 white marbles, you're still completely unsure. So for a specific data set, even within a high-powered experiment, you could still be completely in the dark.
But how would a Bayesian solve that? As a
Bayesian, we always condition on the data observed. So,
yeah, okay,
how likely were the observed data on the one model versus the other model? And they're equally likely on the both models. Now,
so
they're both unlikely. Right.
Yeah, but you haven't really learned anything, which was the same conclusion, right? I mean, that's yeah.
No. When you do a high-powered experiment, the temptation is to say, I did a high-powered experiment, so the result will be diagnostic. So if I don't find a significant p-value, it must be that I now have evidence for the null. But that's not necessarily true. It's true on average before you see the data. But a Bayesian always argues post-data. After I see the data, conditioning on what I now know, what can I conclude? And those things often agree, but sometimes they don't.
Right. This is, I think, connected to another statement that I want to make explicit here as well. If I understand you correctly, again, what you're saying is also related to the concept of evidence, right? So one of the things that we've been talking about in this course so far, starting with examples from reasoning and argumentation, are related to when are we willing to call something evidence? Could we say that given that one hypothesis predicts the data accurately, is that evidence for that hypothesis? Or do we actually need a comparison between 2 hypotheses to say that, well, we've found evidence for one thing over another? Mm-hmm. And that's related to what you've been saying so far, right? So you need to make a comparison between 2 differing predictions to say that you found one evidence for one thing over another.
Right.
Which brings me to the statement that the other approach, the null hypothesis significance testing, would you agree, Danny, that doesn't offer us evidence for anything, comparing p-values with alpha levels?
No, the null hypothesis testing, or in general, this type of frequentist analysis gives you error control, but not a measure of evidence. Right. So if you want a measure of evidence, of inductive support, as they call it, you have to go beyond the pure null hypothesis significance testing framework, and you can do that in various ways, but it would generally involve assessing the relative probabilities of data under various hypotheses and weighing these in some way. So if the null hypothesis is true, then we expect this, and if the alternative hypothesis is true, then we expect this, and you have some sort of weighing of that, and the Bayes factor, in fact, is one of the ways of doing that. So I would agree with EJ that if you want to go if you want to quantify evidence, the null hypothesis testing procedure is not necessarily the best way to go. So that doesn't invalidate anything about the null hypothesis testing procedure, because it's not designed to give evidence. It is designed to control your mistakes. And that's, of course, also immediately the response to EJ. How many mistakes does the Bayesian make? How do you know that your type 1 errors are under control?
Right. Yeah. Well, the thing is this, and that's I think this point comes up a lot, right? So we have error control in the classical framework, and there's no error control in the Bayesian framework, right? This should upset a lot of Bayesians, but if you think about it a little more deeply, Bayesians actually achieve something much better than error control. What a Bayesian analysis gives you is the probability of making an error for the specific case at hand. Right? That's the posterior probability, 1 minus the posterior probability for that hypothesis. That's the probability of making an error for the specific case. And what you get from the classical framework, actually the word error control here is deeply misleading, and we talked about that in the chat a little bit. And Roland pointed it out as well in the lecture. You don't control the probability of an error. You control the probability of an error given that a particular hypothesis holds. But if you make a specific decision, you don't know how you controlled your errors, because if you talk about extrasensory perception, Danny and I wrote a Bayesian article about extrasensory perception together, then if you reject the null hypothesis, the probability of an error is basically 1, right? Because extrasensory perception doesn't exist. But there's no way you can get out that number 1 in the frequentist paradigm. You have to make that we know it's 1 because of our prior knowledge. And what frequentists do is they refuse to take that prior knowledge into account. I think that's problematic.
I think you very deeply believe that hypothesis is true, but we don't actually
You
know
too, Danny.
Right? I believe it too, but we don't know it. And I think this is a bit remarkable that you say, well, you get something. So first of all, if I say that it's really nice to have a house, I don't think it's a very good argument to say, well, but we've got a car. I mean, that's nice too. It's also nice to have conditional on the data statements, but it's also nice to have good frequentist probabilities. And I do know that there are some Bayesians, at least, who would say, well, Bayesian statistical procedures should also have decent error control. And I don't understand why you would negate that. And the other thing is that you say, well, we have the probability of an error conditional on the data. But what probability is that? Because now it seems to me that you're talking about the probability and not your subjective degree of belief that you've made an error. No, I think you're talking about the real probability. So how do you get that from your analysis?
In all probability statements are conditional on your knowledge.
Yeah, okay, right. but if you talk about the probability of an error,
given all the assumptions that went into the analysis.
And then what does the probability mean?
That probability means that if you would make a decision and say, I declare the alternative hypothesis to be true, that the probability that would be an error is 1 minus.
Yeah, but what is that probability? The probability that there will be an error. I mean, isn't that the frequentist concept? Don't you mean? So what then do you mean?
Well, it's your. So let's say, for instance, you have 2 hypotheses. It will rain in the next hour, or it will not rain in the next hour, right? And now you have to decide: will I bring an umbrella, or will I not bring an umbrella, right? So then. If you say it's an 80% chance that it will rain, right? Then if you say, okay, I will bring an umbrella, right? The probability that you will bring the umbrella, but you don't need it, is 20%.
Yeah, but what does that mean? The probability that it will rain is 80%. Does that mean that it's Gold's degree of belief or your degree of belief or whose degree?
Always the level of conviction of the person, of set of people who made assumptions in the particular statistical model. So according to the statistical model.
All right.
How can it be any different, right? Let's say, so this brings us back actually to the philosophical discussion, right? So say I toss a coin, right? A fair coin, I toss it. What is the probability that it will land heads, right? So you may say, well, there's just one, right? It's 50%, and that's a fact, right? It's objective. But now let's say I toss the coin, and just before I toss it, you see that it is heads up on my thumb, right? Well, then you actually know, if you know the literature, that the probability that the coin will land also heads is not 0.5, it's 0.51, right? You can go through the physics to show that it's about 0.51, right? So, so for the person who looked at that coin, right, it's now 0.51. Another person may look at that coin but not know the literature. So for that person, it's 0.5.
Yeah, but it's actually 0.51.
No.
And it's actually 0.51.
No, it's actually 0 or 1, right? Because when you're God, or when you know the physics, it's you know, you can predict with perfection, right?
Yeah, but
so that
what
means,
I mean is, what are you talking about when you say the probability is 0.51? You mean that if you did the experiment a lot, you would find
no. It's your degree of, it's your intensity of conviction that on that particular throw, the coin would come up 0.51.
All right. So
because
not because of any frequentist considerations at all.
I'm going to step in here. I'm going to try and give a brief summary of what's been discussed so far. So we started talking about error control, and the error control in the frequentist procedure is very explicit, right? So in an ideal scenario, you would think about how dislikable different types of error are to you, and you would adjust your procedure accordingly and make sure that the probability of type 1, type 2 error is low, and that has a specific interpretation that you will be wrong in if you act this way given this procedure, that in such percentage of cases you will be wrong given that the null is true, and you will be wrong in such percentage of cases given that the alternative is true. Erik-Jan then tried to indicate, or he indicated, I'm sorry, I don't want to be put a value judgment in there, that there is a form of error control in Bayesian statistics as well, in how you, well, I assume act on the output of your analysis. And then he asked Erik-Jan, what do you mean? What does that probability mean? And then we started talking about, or they started talking about what probability means in the conception of Bayesian statistics compared to frequentist statistics. Because in the frequentist approach, it's clear, right? You should decide in this way, you should decide in that way, and deciding in that manner has a certain error rate. In Bayesian analysis, there is no such decision, but there's a change in your degree of belief.
Well, you could make a decision in a Bayesian framework as well, right? It's not that frequentists have the sole rights to making a decision, except if you want to make a decision in a Bayesian framework, you first have your evidence, right? Well, actually, you first have your prior knowledge, you combine it with the evidence, you get posterior knowledge. This is your current knowledge of the world. And then if you want to make a decision, you need to say, okay, what are the utilities for my particular actions? How bad is it if I forget my umbrella and it rains and I get soaking wet? How bad is it if I bring my umbrella and it doesn't rain? The annoyance of having to carry the thing around. And on the basis of those considerations, you can make a decision. And the problem that I see with classical statistics is that they go straight to the decision instead of first saying, what evidence is the decision based on? Right? It's just one big blob, one big decision-making thing without neatly compartmentalizing what is prior knowledge, what is evidence, what is utility, and then making a decision. Sorry for that interruption.
I would say that's the fact that these things should be teased apart and should be considered, I would agree with. And I would also agree that null hypothesis testing actually lumps that all together. That's a price you pay. There's always a price you pay, right? So there's no such thing as a free lunch. Any statistical procedure brings with it assumptions and has certain goals that it realizes in certain situations. And if you're out of these situations, yeah, you're screwed. So what are the problems of the Bayesian actually in this respect? I've now, and that's a generic issue I have also. I mean, there's a lot of problems with frequentism, and there's a lot of problems with null hypothesis testing, and frequentists are generally very aware of that, and are also, you know, we also teach, you know, how you have to interpret the p-value and how you shouldn't. So what do you think are the big dangers of comparing? If everybody started to go Bayesian, what do you think the main psychological problems would be? You know, it's still humans, so they will, as you say, anything can be abused. What are people most likely to succumb to? Which biases and which problems?
Yeah, I think by far the mistake that most people make when they use Bayesian statistics is to mistake the evidence for the posterior belief. Right? So you see a Bayes factor, let's say you're looking into extrasensory perception, and you see that the alternative hypothesis outpredicts the null hypothesis by a factor of 5, right? And then people misinterpret this result by saying, oh, it's now 5 times more likely that extrasensory perception is true, right? And that's not the case. Because you have to take into account the prior plausibility of these hypotheses. So if extraordinary claims require extraordinary evidence, right? And that statement is sort of almost the formalization of Bayes' rule. And if you ignore that, then you can get conclusions that are very rash, right? Premature. But you know, there's actually a long list of mistakes that people can make in Bayesian inference as well, right? Multiplying Bayes factors, even though the data are dependent, and yeah, there's tons of stuff you can do wrong. You know, unfortunately, shifting to a different statistical paradigm won't suddenly make people good statisticians. So I think we have to really work on the educational part.
I think we have found a point of agreement, at least here. So I'm also wondering what the other people think. I mean, there's a lot of people.
Yeah, we should bring the students in. We should bring the students in. We always do that, but we kind of got, sucked into debating amongst each other.
I see a lot of chatting about my dog, but that's not what the debate is about, people.
Yeah, let's hear it from the students.
Can I ask a question?
Yes.
So as I understand it, maybe I'm wrong, but the main argument here is a little bit that with frequentist statistics, if you find no evidence for the alternative hypothesis, you basically end it there. The research is kind of ended. And with the Bayesian statistics, it is a little bit more dynamic. So you still account for the error, or for the possibility that that is wrong or could be wrong, that there might be an effect, even though we don't find it. But still, it is not entirely sure where it is. We cannot be 100% certain, right? And with the frequentists, with the Bayesians, if I get it correctly, it is more that because you constantly testing, and even if you kind of see that there is no effect, you cannot be 100% sure as well, because it is also possible that your sample just was unlucky, kind of. So that's why you do it again. Is that kind of correct, or am I completely wrong here?
So to come up with to enter the first part, if you do a frequentist procedure, and you fail to refute the null hypothesis, well, that's basically where you end. You say, well, I haven't refuted the null hypothesis. You could, of course, say something like, I had a really big experiment, I had a lot of people, I had a very high power, and despite all that, I didn't refute the null, but still that's where it ends. If you want to say how much more likely is the null hypothesis than the alternative, you have to have some sort of quantified measure of the probability of a hypothesis, and so you have to turn Bayesian. So that's basically the situation.
So
But
at one
isn't then a
point,
combination good? Wouldn't a combination be beneficial then, that you have frequentist statistics on the one hand, but if you're not sure if what you found might be valid, you do the frequentist and then you do the Bayesian and then the frequentists again?
I'm personally a robustness freak. So what I always do when people ask me for methodological advice or I'm doing research myself is I do everything. I really do everything. So people say, should I do a t-test or should I do an ANOVA? I do everything. I'm like completely promiscuous in this respect. I use every single statistical method, and then I see, what centers on the same hypothesis and what are situations, what deviations do I see, and how do I weigh these? I think Sharon.
You're being accused of being a p-hacker in the chat.
No,
Yeah.
no,
no.
It's not true.
It's not true, and I agree with Danny. Promiscuity in for a methodologist is a good thing, because there's a difference between a robustness check and cherry picking, right? If you're cherry picking, you're doing all these things and then selecting the one you like best, and then everything else goes out the window, right? That's bad. But showing openly and transparently, this is what you get if you apply alternative methods of analysis, that's really good. So the secrecy is what makes you a p-hacker.
You have to be
I
open
do
about
want to
your
go, I do
promiscuity.
want to go
for this,
back
right?
to one of the points that you made earlier, Danny, because you said, well, within frequentist statistics, if you don't find your result, you're not able to review your null, then you're done. And
with the frequentist part, right? With the null
okay,
test.
sure.
You can do other stuff, of course. You should.
Yes, of course, but your one experiment could be the fluke. The within the 5%. So actually, you should say, well, I need to replicate. But and that is the point that you're making, of course. That if you have robustness, then if you provide different methods to get to your results, then at one point you will find.
No. But this is
you will find it.
But this is a really important thing. So I got an email once from a professor from the US, right? A major player in his field, and he said, I have this problem. I just ran an experiment and it has a lot of participants, and my crucial effect gives me a p-value of 0.051. What do I do? Well, what I advised him to do is a Bayesian analysis, and then the evidence won't be compelling, but at least you can just add participants, new participants, and continue the learning process, right? And then he replied something like, too complicated, I'll just throw away the data and have my students run a new experiment, right? And so that's bad practice, people. That's bad practice, because those data were information and you don't throw that away until you get the result you like.
Can I? So this is really important. This is more important actually than Bayesian frequentism. So what EJ just said, secrecy is a problem. So it's really, you really should not get the idea that, if you just follow this and this and this best procedure, right, then you're sort of, then everything is okay. It doesn't work like that. So if you say what you're doing and you're frank and you're honest, you can do anything you want, including p-hacking. Actually, I would like to write a book, p-hacking theory and practice, and how you do it, and just tear your data apart. But, right, you should not interpret, if you get a significant result then, as evidence for your hypothesis, right? So that's the difference. It's interpretation and being open about things. So don't be superficial in the sense that you think that if you follow the right rules in the cookbook, you always end up in the right lane. The deep principle is openness and thoroughness and honesty.
Go back to my question for a second, because you said now, Danny, that you do it, like you go do all the tests basically. But what would happen if you generalize that? So if everybody would start doing that?
I think that would be a really good idea. And I think people should actually pre-register, 1,000 analyses and, you know, do everything. And that's all fine. There's no problem. As long as you make clear that this is part of the methodology you report.
Yeah.
Yeah, another really good.
I want to interrupt for 1 second. Danny, could you elaborate more on what the robustness means? What that word means?
For me, I don't like it when I have a conclusion. So I'm in these networks, right? Maybe you've seen that. There's a zillion ways of doing these networks things nowadays. And if you do it, so I don't like it when I have a conclusion that depends on one particular network estimation procedure. I just don't like that. I want to know that that the result is robust if I change from this procedure to this procedure, because, you know, the change is irrelevant theoretically. And that's what I think is generally also how you should think about statistics. If the difference between a non-linear and a linear effect doesn't matter for your theory, then you should not be in a situation where you find the effect if it's linear, but not if it's non-linear or something like that. You got to be robust against trivial changes. That's what I mean. I think you could have, you can do an experiment, right? And you can say, well, if this theory is true, then we expect this to happen. And we can run this analysis or that analysis or that analysis and that analysis, and we expect all of them to converge on this result, right? That's and then, yeah, if you want to know how strong that evidence is or how plausible your hypothesis becomes, well, then you have to become a Bayesian.
Yeah,
I will give EJ that.
But the thing I believe, and Danny and I are in complete agreement, I believe, on this point, is that it's important to distinguish the confirmatory aspect of your research from the exploratory part, right? So in a confirmatory test, you specify in advance what you're going to do, and part of that confirmatory test could be, let's explore the robustness of this phenomenon.
Exactly.
Right? But that shouldn't be confused with an exploratory data dredging exercise, right? Those things should be, if you do data dredging, right, and you just look at everything, then what you get, like Danny said, it's not evidence for your hypothesis. It's a hint, it's a suggestion that if you do a new experiment, this may be worth looking at.
Yeah, I want to summarize what we've been talking so far in response to the questions by Maurice and the suggestions by Noah, is that that the core of agreement actually between Erik-Jan and Danny is that robustness is important, right? So the fact that your results and your conclusions are not dependent on one very idiosyncratic specific way of doing your research and analyzing your data, but that you can show that it doesn't matter who does the research, in whichever method, whatever sample, you get the same results, and then you have robust results, and that's a core important. That's goal. That's the important goal for science, right? That it doesn't matter what you decide; it will show. The reality will show itself in that way. If I summarize correctly, you're in agreement on that. That would be. It doesn't matter which approach you take. But what I want to ask specifically about that, relating to the statement, is what we've seen so far in the problems with null hypothesis significance testing is that people have difficulty in, well, getting a properly judging how robust those results are. So it's very difficult to know what could have happened but didn't, depending on the choices you've made, right? So even if we're not trying to be sneaky and explicitly striving to be p-hackers or cherry pickers, it's still difficult to keep that perspective in mind, right? If I did use a different dependent measure or used different groups, but material, something else could have happened, right? And isn't null hypothesis significance testing more sensitive to those errors in thinking than the Bayesian alternative?
But especially if you would do the Bayesian statistics in the sense that you run your experiment once and you stop and you conclude on only that set of data and your fluke for that matter.
Yeah, I don't think so. I think those issues are problems with the fact that it's not robots who do the statistics, it's people who do the statistics, right? So we are subject to all kinds of biases, and as psychologists, we should know very well what those biases are, right? Hindsight bias, motivated reasoning, and Francis Bacon already wrote at length about the fact that humans aren't actually very good at doing science. We need a method to control our biases if we want to draw reliable conclusions. So the methodological tools we can use is pre-registration, which commits us to something beforehand. And another recent development that I like very much is a multi-analyst approach, which means that you have your data, but you share it with independent group of researchers who all analyze the same data set and send in their reports, and everything is published together, right? Which at least means that you get a better idea of what other analyses are plausible and could have been done. And it also means that you get an idea of what people would do who aren't as involved in the research as you are.
Right.
Yeah, I think this is dangerous, EJ. We're gonna agree on all of this.
Yeah, we went the problem started when we started to talk about questionable research practices and transparency, because we agree on that so much.
Yeah.
Too bad.
Right.
We'll try to disagree more next year.
So what I want to zoom in on is perhaps a specific.
Sorry.
Yeah, go ahead.
Could I ask something real quick? Because there's a question in the chat.
Yeah.
It's for Danny. Tara says, you said before that complicated tests such as mixed ANOVA are really hard to do with Bayesian statistics. Oh, no, it's for EJ. Sorry. What is your response to this, EJ?
Oh, yeah. Well, thanks for reminding me. So it depends on what you want to do. If you just want to estimate parameters in a statistical model, then it is nowadays with the new numerical techniques that are available for Bayesian inference, it's actually easier to fit complicated models than in classical statistics, right? You're limited, the Bayesian modeler is limited only by his or her imagination. So in fact, there are hardcore frequentists now who are using Bayesian methods because their models converge and work under that framework. So if you just want to estimate parameters, draw nice posterior distributions, it's easier. However, if you want to do hypothesis testing, then the prior distributions become really important. And in complicated models, it's often more difficult to insert specific prior knowledge on those parameters. So then you have to use default choices, and I wish it were easier.
By the way, I am occasionally, I'm a pragmatic person. EJ is correct that Bayesian modeling approaches offer possibilities that frequentists struggle with. So that's definitely the case as well. But yeah, and I would also expect EJ, it's a bit of a beginner's problem, right? So frequentism has been sort of rolled out from the 1940s. And Bayesianism basically really became computationally feasible in the late previous century, I think.
Yeah.
That's when it started
1990s,
growing.
1980s. Yeah.
Yeah. So you would expect this to be solved within a few years?
That's actually one of the things we're trying to accomplish here with JASP, right? To develop popular analyses that haven't had their Bayesian implementation yet, and present them to people so that they can easily be conducted. And in fact, I didn't mention this, but JASP actually also includes a lot of the network approaches that Danny has championed over the years. So,
yeah, thanks for that.
Well, but it's the same principle, right? You have a new approach that people are unfamiliar with, and it requires some technical know-how and some programming expertise. But if you really want to make people use it, you need to implement it in a piece of software that's easy to use. Otherwise, it's going to remain fringe forever.
Egan, just to tap in to ask you a specific question about what you said. So if I understood it correctly, you're saying that that it's sometimes complicated to quantify your prior knowledge, right? Or am I summarizing you correctly?
Well, for a complicated model with very many parameters, right? I don't know if people have had structural equation modeling in this course or earlier.
No. Okay.
Well, sometimes you have complicated parameters that relate to latent constructs that are related to each other again, and also like prior distributions for matrices, covariances, right? That at some point the human mind cannot assign really informative prior distributions. What you could do is you could say, I have my model. I'm going to fit it to a small representative data set so that I update my vague opinions with this data set. And then the posterior distributions that I have, those will become the distributions that I use for my test. But you can't, the thing is, you can't specify something vague and then do a test, because what the test assesses is how well did you predict. And if you don't make very many predictions or super vague predictions because you don't know what you're doing, you're just simply not ready to do a test.
Right, but you could do a null hypothesis significance test, and that would be my specific question. In that scenario of vague predictions and not being ready to do more specific analyses, would the psychologist be better suited with doing a null hypothesis?
Well, that gets back to what we actually learned from that p-value, right? Danny had this fantastic slide. Actually, Danny, I'm going to show people my slide here. Can I share my?
Oh no!
Can I share my screen? I forgot to do this
you
year.
Really take it all.
It's the devil screen.
So this is that screen. So I took Danny's example from the logic of the null hypothesis test, and then you show this the story of how it unfolds, and right. And so Jack basically gives a p-value, and then Jim kind of agrees. Oh, so if I were to repeat this experiment infinitely often, blah, blah, blah. But that's just the definition of the p-value, right? So Jim should actually continue the conversation and say, so what, right? And then Jack would just say, well, didn't you listen? This is the definition of the p-value, right? And then the question, so what, right? And that's a very difficult question. The so what question is very difficult, I think, to answer for a p-value, because ultimately what you want to say is, I now doubt the null hypothesis. The null hypothesis is now in doubt, right? But that's a dangerous word, right? Because doubt is awfully close to something related to belief or convictions, right? And prior beliefs and convictions should...
But I can say things about my beliefs, right? It's not like I don't have beliefs. It's just that my beliefs don't operate, as far as I know, according to this simple probability calculus. My beliefs are very... it's not so easy. I think yours are neither. So as a mathematical psychologist, you don't seriously believe that's how we do it, right?
Well, I do think that accounts that predicted the data well become more plausible, and accounts that predict the data poorly become less plausible.
Okay, but I can still say that.
So you're willing to say, if you have a significant p-value, that the null hypothesis is now less plausible than it was before?
If I have a large sample and I have enough power, and I wouldn't put a number on it though. So I wouldn't say I have the probability, right? But I think obviously. I mean, that's what I said earlier. There's no magic, right? There's the design, there's the data, and there's the sample size in a standard experiment, and that's all there is. It's all on the table. So you can become really complicated with all your machinery, but in the end, what you're saying is the same thing.
Right. No, but but this is exactly the point, right? So if you have a significant p-value, let's say 0.03, you now believe that the null hypothesis is less plausible than it was before. I think as a frequentist, you have to say, no, I can't address that question.
Yeah, so that's what I'm going to say.
Yeah, but see, that's the problem. Because I think that's actually what you want. If you can't even say that, if you can't even say that the data made your null hypothesis more or less plausible than it was before, what are we doing?
Well, what we're doing to answer your question in that hypothetical conversation between Jim and Jack is, well, so what? Well, I've played the devil's advocate, and assuming that it's just, I don't know, random noise, this would be this, or more extreme than this would be highly unlikely.
That's the definition of the p-value.
Exactly. But
so what have we learned about the null hypothesis?
We could continue that conversation and say, well, that's an interesting first step. Let's do some more research. Or
But what is interesting about that step? What is interesting about it?
We're learning something about getting an effect size for this experiment. So if we...
Sorry, Sharon, you're
Oh, sorry. So if you replicate the experiment, you get another effect size. And if you replicate again, you get another effect size. So you're essentially getting a better sense of what your alternative distribution in that fact would be.
Yeah, but we're having we just had one experiment, right? I don't know what it is.
Yeah, so that's my point. You shouldn't base your decisions on your one experiment. So either in the frequentist way, you should replicate and make sure it's not just one decision based on one experiment. So you should replicate your experiment multiple times. And within the Bayesian frameworks, you should update your prior.
But this is what you're saying here is this is revolutionary, right? You're saying you cannot draw conclusions from a single experiment when you use frequentist statistics. That's what you're saying.
Yeah.
But isn't that what you're doing? Sorry, but isn't that what we're doing? Because every research paper we're reading, I was wanting to ask it for like half an hour, but everyone was always talking.
No problem.
But isn't that what you're doing? Like that's exactly what we're also writing when we write research descriptions. I mean, we have like several papers that should lead us in a certain way, and we explain why it does lead us there. But we conclude at the end of every research description, this and this has an effect on that and that, and you say that we cannot actually say that. So we are lying all the time, basically. Because on every end of
you're making a decision in a procedure, which will mean that you're not wrong very often, given that something or other is the case.
Who wants to know this?
We're writing, right? That's not what we're writing. We write at every end.
Yeah. No. But no, Anne, you're completely right. What you write is a conclusion for a specific experiment, and the conclusion is definitely not phrased in terms of if we were to do this very many times, blah, blah, blah. No, people just say there is an effect.
Yeah, that's real.
Or there is no effect, right? Because that's what people want to know.
Yeah, but that's also, yeah, that's really, I would say that's a real problem. And the Bayesian, if the Bayesian affair seduces people into believing that you can actually, give these big claims from a single experiment, would you say that's a good thing?
Well, it's not a big claim. It just says which hypothesis predicted the data better, and if it's the null, then now the null is more likely than it was before. That's not. The thing is, if you find that people use a screwdriver to get nails into a wall, it suggests the need for a hammer, right? And the same thing here. If people continually misinterpret the p-value to mean something Bayesian, right, it suggests that people might be better off adopting, as well as a classical approach, a Bayesian approach.
But just to tease two things apart, a frequentist can also say the data are more likely under this hypothesis than under that hypothesis. That's called the likelihood ratio. Yeah. There's nothing wrong with that.
No.
So you don't have to be a Bayesian for that. That would be an overstatement, right?
I agree. Likelihood ratios are basically the base factor is a generalization of a likelihood ratio to hypotheses that aren't points. So the likelihood, I think this is also something that Danny and I agree on. The likelihood, the predictions for the data under a particular hypothesis or parameter value, that's the central concept that unites the Bayesian and the frequentist approach. They both use likelihood.
All right, so we're running over time because we started late. For people that have to leave, you can feel free to leave. There will be the recording afterwards, so you can check out those final couple of minutes. But I do want to tie this back into the stuff we've been talking about in this course so far. So we've debated a couple of issues. We've talked about the goals of the differing approaches, about the differing approaches and Bayesian and frequentist, and what it has to do with QRPs, with sensitivity, with error control, with evidence and mindlessness, in the sense that unfortunately, as Erik-Jan put it, not all psychologists are trained statisticians, and that could lead to wrong use of statistical procedures in any approach. And I'm summarizing here because I want to give you students the opportunity to ask additional questions about anything depicted here or anything else that might have come up as well. I hope that Danny and Erik-Jan still have some time to get into some questions.
Yeah, so I think there were quite a few questions in the chat already.
Right.
So
yeah.
maybe people can who have been posing questions in the chat but didn't see it answered could ask these.
Right.
So one interesting is did I miss? Daphne says maybe Daphne wants to ask her question herself.
Yeah, I had a question about picking the prior for the base. So where do you like set the line between arbitrariness and subjectiveness? Like how much evidence or how much prior research do you have to take into account to set an accurate prior, and what effect is it if you would just like pick it completely arbitrary?
Yeah. Now, so there are cases in which it's quite clear what prior you pick, right? For instance, you've done experiment 1, and now you do a replication experiment, and you want to keep experiment 2 as close as possible to experiment 1. So it makes a lot of sense to use the posterior distribution from the first experiment as a prior distribution for the next one. For more generic cases, well, for instance, what we've looked at is okay, there's several choices. You can choose the default prior distributions, right? Those have general desiderata that are nice, so you can use those. And I often use them as a reference style analysis. So this is what you would get if you were to use the default. And then I check robustness of that result by using a more informed choice. And one of the things we've been doing lately is to elicit prior distributions from experts. So before you conduct a particular experiment, you talk to the researcher and you say, what effect sizes do you expect approximately? And there's all sorts of tools that you can use. We usually have an interview of about an hour, and then we extract some kind of expectation from the researcher, right? And so only going with that expectation is really dangerous because it's usually very precise, overly precise, and it could be all wrong. But you know, when you have several researchers who say more or less the same thing, and you see that it doesn't matter for the conclusion, right? Your base factor could be 50 or 100. It doesn't matter whether it's 50 or 100, right? It could be 50, 80, 100. When I see those numbers, 50, 80, 100, I say this is very robust. The numbers are different, but the conclusion is exactly the same. Really strong evidence for the alternative hypothesis, say. What is tricky is when you have plausible, reasonable prior distributions, and they give you very different results. Right? Now, what do you do then? Well, you openly acknowledge it, and you say the data aren't strong enough to give us a conclusive answer. What you don't do is say, let's just pick one, or the one I like best, or let's just conclude that Bayesian analysis is horribly subjective. Right? You don't shove uncertainty under the carpet. You openly present it. And I think that's the basic job of a good data analyst. And the temptation is always to remove uncertainty, but the goal should be to acknowledge and quantify uncertainty.